Okay, today we start this class March 25th, right? This class of thermodynamics, the second part. We will do some problems. We will solve a few problems. Remember the last class we saw the mechanisms for transmitting heat, convection, conduction, and what's the other? Natural convection and radiation. There is natural and forced convection. You have to remember that. But we will not analyze in deep detail heat transfer here because heat transfer is a full course. I just mentioned for you to know, to understand that these things exist, that the difference between heat transfer and thermodynamics is that thermodynamics study conditions of equilibrium. Let's say you start from condition one, and you reach condition two. This condition is in equilibrium, and this is another equilibrium. And you study what has to happen for this change to occur. In heat transfer is different. Heat transfer, you really study the process here. Process. So we will not see in detail heat transfer. Maybe I will mention a little bit issues about heat transfer. I mentioned already last time the mechanism of heat transfer. With this guidance, I will review a few concepts of what we saw the last time. The last time, we saw thermodynamics, and we saw this machine. And we say that the heat goes from hot to cold, and then you can use this for generating some work. Okay. I forgot if you have some homework, no? Maybe, or you forgot. For next week. Next week, okay. That's for the seminar issue? Okay, anyway. So anyway, naturally, the heat flows from high source to low source, or low temperature source, which is more properly called sink, and this is more properly called the source. And if you want to reverse this, if you want to reverse in this direction, then you have to input work instead of, you cannot extract work, you have to input work. And this is what the refrigerator does. This is what the air conditioner does, and so on. Then we saw that the last time. We didn't analyze the Carnot efficiency. I think maybe in the second half of the class, I will explain what is the Carnot efficiency. The Carnot cycle is something which, well, of course, I think since it's more or less advanced thermodynamics that part, I don't know if we should touch it, but still I can mention it. So if we can find a boundary through which there is no flow of anything, if the heat doesn't flow, there is no flow of heat. Yeah? This process is called adiabatic. Adiabatic. Then when you listen the word adiabatic, it means zero flow of heat. There is no flow of heat. There are some systems where approximately this happens. You have a glass, this glass which are where you store the coffee. You have this I don't know how to call them, thermos in Espanol. In Spanish is termo, huh? I think it's Stanley. Well, anyway, some kind of glasses or so, but they isolate they store very well the heat. Well, that's not the correct way to say, but that's approximately an adiabatic system. The heat escape very slowly. So that's why you can keep it the whole afternoon or the whole morning and still. So that's an adiabatic system, okay? The flow of heat is negligible. That's the idea. In our convention, remember the first law of thermodynamics? It was Q plus W equal change of internal energy. Something I didn't mention to you the last time is that the internal energy measures of course, the energy, intrinsic energy of the system, which is kinetic and potential energy of the molecules inside. No? You have a gas, for example. The gas have kinetic and potential energy. Please measure it. And we say that for a gas, the change of internal energy is the mass, heat capacity at constant volume, well, more properly the integral of this. And if this is approximately constant, this is mc delta T, change of temperature. The same for solids, but in solids, we use C because Cv is approximately Cp. Remember the heat capacity at constant pressure and constant volume. We defined the last time. Which one is larger? Do you remember? Which one is larger? Heat capacity at constant pressure or at constant volume? Do you remember? Heat capacity heat capacity is the amount of heat you need to introduce in a system for increasing the temperature in 1 degree. So which one? Remember that when the pressure is constant, the system wastes part of the energy in the expansion. So it's more difficult to increase the temperature, so Cp is larger. So it takes more heat to increase the temperature in a gas which is expanding than in a gas which is not expanding. So this is the way. That's why I say to people, you don't have to memorize. Physics is not about memorizing things. Physics is about understanding things. Mathematics is not about memorizing things. It's about understanding things, which is a problem I have when I teach. Well, you are a scientist, here is a science, but when I teach to guys of other faculties, mathematics is an issue because they try to memorize. Mathematics is not memorizing. You have to understand it. Read the theory. Read the theory, don't blame the professor. Read the theory because if you don't read the theory, you will not understand. The professor can give you some clues here. He do what he can, but there are many other things which are in the books only. And there is no space, enough space to say everything here. So we will do this six kind of problems later using the first law of thermodynamics. We will evaluate changes of entropy also in some systems by using the formula. Remember the formula of change of entropy. It was the integral of the change of heat divided by temperature. And of course, if you have this from here, you can introduce and change, calculate change of entropy. When there is a thermodynamic cycle, the first law of thermodynamics is equal to what? In this case, 0, because the cycle repeats. It goes to the same point at the beginning. A cycle, let's assume, imagine a piston expanding. You have this. This is the piston. The gas is here, and this is the camera. Where do you see the system? In the cars. The engines of the cars, they have pistons. They move so fast that you will not be able to see with the naked eye exactly where the piston is if you are able to see inside the camera. But this goes back and forward, back and forward, back and forward. This mechanism is called, in Spanish, is manivela via la corredera. Is basically this rotates, and this converting rotational motion in linear motion. These kind of conversions are very useful. There is a lot of physics, mechanical physics here. But of course, we will not see those details here. But we care for the moment is that this cycle repeats. The piston was here once, and it will appear here again subsequently. Every time the cycle repeats 1 point, the change of internal energy is 0. And that's why I was telling you the last time. So it means the heat is the negative of the work in that case. Because the thermodynamic properties don't care how you reach that condition. If you reach that condition again, the change is 0. But the heat and work, they care the trajectory. Because I can create another system where there is not this gas or so, but I still come back to the same initial point as here, and still this part will be 0. The work will be different from 0, but the heat probably, there will be other combinations of heats now also. So, I mean, my point is that in a cycle, the change of internal energy is 0. So we saw that the last time. And there are some few concepts which I have to mention. There are some thermodynamic processes. Look, adiabatic process, where these letters are quite small, but when I mention in the video will appear clearly. Adiabatic is what I just said. There is no heat flow through the boundaries of the system. It's an isochoric process. Is where the change of there is no change of volume. Let's say when you fix the volume of a system, and people say this process is isochoric. For me, it's not important you memorize these terms actually, but it's important to mention anyway. Isobaric process is constant pressure, and isothermal is, of course, constant temperature. There are processes, thermodynamic process, where the temperature is fixed. I will make you an example. What is the temperature now in the environment? 27. Well, do you think it will change in 1 hour or in the coming 2 hours? Appreciable. Maybe it will keep constant for a few hours, no? At least. So this is, I mean, any process happening around related to that temperature will be isothermal, for example. Or whenever you keep a camera fixed at some temperature, that's an isothermal process. So thermodynamic equilibrium, we saw it because it was the zero law of thermodynamics. You remember the last time. Thermodynamic equilibrium is reached when there is not much more flow heat, of course, and the temperature of the two systems is the same at the end. And we saw the example, I put a glass of water and I throw some ice here. At the end, the ice will melt. The total entropy of the system will increase. They will exchange heat each other. The ice will absorb heat. The water will lose entropy. The ice will increase the entropy because it will melt. And at the end, there will be a thermodynamic equilibrium. Final common temperature. And these problems are easily solvable. We will solve one of these problems in a moment. We only have to search a few thermodynamic properties like the heat capacity maybe of ferrium or so. Well, we will see in the coming example, which I will do it. We defined enthalpy the last time. Sometimes it's convenient. Enthalpy is internal energy plus times pressure volume. Sometimes the certain thermodynamic processes, especially those happening at constant pressure or so, the concept of enthalpy is useful. Sometimes we can use the internal energy, we use the Helmholtz free energy, or the enthalpy Gibbs free energy. All these concepts are related via something called Legendre transformations, which we will not see here because it's outside the scope of the course. But you should know that why this is important. For example, the Gibbs free energy is important in chemical processes because whenever the Gibbs free energy reaches some, let's say, extreme conditions, maximum in principle or minimum, then the chemical process stops. So these extreme conditions, technically, in a system, any process should stop when the entropy, for example, reaches the maximum, because the total entropy has to increase. And when it reaches the maximum, and it's going to fall to a minimum, well, the Gibbs free energy behave more or less the same. Well, it's another kind of thermodynamic way to see that. Yeah. We will not see that in detail. These are examples I don't want to address. The zero law of thermodynamics we saw, the first law of thermodynamics we saw, etc. Now let's search some thermodynamic properties here. We'll search heat capacity, water. The heat capacity of water, I will copy here, is 4,200 joules per kilogram per degree Celsius. And now I want to copy the heat capacity of, let's do the iron, better, iron. Heat capacity of iron. But it says 0.0 We can compare it anyway. The capacity of iron is 0.45 is joules divided grams. If I want to convert to kilograms, what should I do? 1 kilogram is 1,000 grams, 450 joules, kilograms, degrees Celsius. I can tell you that it doesn't matter if this is in Kelvin or Celsius. It will be the same quantity. And the reason is because the changes in temperature in Kelvins and Celsius are the same. And the heat capacities are defined in changes with respect to changes in Celsius and Kelvins and so on. Then that's the issue. Now, based on that, let's do an example. Now I will switch on the lights. Let's switch on the lights. Let's do an example. Let's invent something here. And let's see how is your logic here. I put a tank here. This is water. Well, the water should be blue. A temperature of the water, tell me some temperature, like 20. Okay, 20 degrees. I put a very, very hot metal. Let's assume that it's more, very, very hot. Tell me a temperature like 108, okay. Or 84, which one? Democratic, okay, 100. Okay, and it's 110, let's put. Then let's put the metal is here. Is iron. Is 110 degrees Celsius. Then I want to analyze the thermodynamic of this. I want to apply the first law because I want to see what is the final temperature of this combined system. What do you think you do? First law. What does the first law say? Is there any work here? No work. Of course, the metal more or less, when it's hot, it expands. When it's cool, it contracts a little. But this is so negligible that nobody cares. I mean, nobody really cares this kind of work. So there's no work. So there's only heat transfer. And then the first law of thermodynamics is telling us that the total heat is equal to the change of internal energy. So in other words, what we will do is to measure the changes of internal energy of each one, the iron and the water. Then, exactly. And something important is the final temperature is the same. The final temperature of this guy and this guy will be the same at the end. So if I have the initial temperatures, I should be able to find the final temperature, assuming that I give you the information of the heat capacities, which many people work for us in the past and date. And they, of course, they calculated this for us, for sure. And I have to tell you that the heat capacity is not constant. In some ranges of temperature, it's approximately constant for some materials, but the heat capacity changes with the temperature. But here we will ignore that because sometimes these changes are not. In the case where there is a phase transition, and we will explain what is a phase transition, that's very important because I think you apply in your daily life and it's impossible that we cover thermodynamics and we don't talk about phase transitions. We'll talk about first order phase transitions, where there's a discontinuity in some thermodynamic properties. For example, when the water melts, the volume of the water is much larger than the volume of the ice, no? That there's a discontinuity in the volume. The same when it becomes gas, no? Of course, it can spread everywhere in the room. The water cannot do that. Okay. Then, of course, phase transitions are important, but here we will not consider these phase transitions here because it's not necessary. I don't think the iron will melt at 110. I don't know actually what's the temperature for melting iron, but I think it's too low for melting iron because 100, the water for sure evaporates. Add atmospheric pressure. Pay attention, because if you increase the pressure, and we explained that the last time, the temperature at which the water evaporates is larger. If you decrease the pressure, it's the opposite. It will evaporate at lower temperature. That's why when somebody asks you, let's assume somebody asks you, at what temperature the water evaporates? Then you will say, it depends on the pressure, or it depends on the location. Because if you go to La Paz, Bolivia, where the football players die when they play, you remember they cannot breathe so well and so on. Bolivia has an advantage there. It's not the same as, I mean, you boil water there and you boil water here at the level of the ocean, as we are in Macau. Where do you think the temperature of evaporation will be larger? There or here? At the sea level. Exactly. Exactly. Here, 110, assuming atmospheric pressure, a little bit of water will evaporate, a little bit. But I think that there will not be enough time for losing so much mass. Of course, if you want to be rigorous and then you want, so the mass of the water will disappear. No, but it's extremely negligible. Then let's apply. What is the change of internal energy of the water? Assuming a constant heat capacity. Let's put, okay, let's do it in order here. Water. It will be the mass. I have to give you the mass of water. I didn't tell you the mass of water. Well, let's assume some mass. It depends on the volume, because of course with the volume you can calculate, but let's put some number. You have some number in mind? You manage fishes here? Huh?
I said 1 kilogram for 1 liter, so it would be simple as possible.
1 kilogram, okay. Then let's put 1 kilogram for the water. This is water. And for water, Cp is approximately Cv, because these fluids are called incompressible. Incompressible, it means, let's assume you execute a pressure on the water, it will not contract so much unless the pressure is catastrophically high. And even if you hit the water, the expansion will be not like the mercury, in the thermometers. And something important about the water is its behavior between 0 to 4 degrees. I will comment about that in a moment, but what happens between 0 and 4 degrees? What happens when the water gets frozen, for example? It expands or it contracts? Expands. The water expands when it gets frozen. That's why your glass gets broken. Put a glass of water in the refrigerator, and I have done that many times because I want to cool some water which is hot quickly, and I forget. Sometimes I forget that I put the glass inside the fridge, and when it's down, the glass is broken. And that's very important for the biology, because otherwise the life in the ocean would not exist. You should know that the reason, precisely because it expands, what happens with the density when an object expands? It becomes lower. Low density, what happens if you put a low density object in the water? It flows, it will to the surface. So that's why when the water starts to get frozen, the ice goes to the surface. The surface is covered of ice, and below still the life is possible. If this doesn't happen, the ocean will start to get frozen from below the bottom to the up, and all the fishes will die. So this behavior of the water is fundamental for the life in the ocean. It's something that not so many people know, but it's important. Later, when we saw buoyant force, you will see, we will analyze the percentage of icebergs inside the waters and these kind of things. Okay, coming back for the moment to this. Okay, change of internal energy of the water. Let me. I think the battery of the computer is critical. Let me connect it. 1 second. Because if not, this recording will be damaged. Well, I don't have an extension here for. Extension is quite far here. Let me see. The screen. Okay, I can steal it for a while. The connection here. Still, we have 25 minutes before the break, so it's okay. So it's connected now. The battery will not die. Then let's put it in this way. Change of internal energy of the water will be mass of the water more properly the integration heat capacity dt. So if you take the heat capacity constant will be mass of water, heat capacity, change of temperature. Because this integration is from initial temperature to final temperature. And the final temperature will be the common temperature between these two guys. Now, let's write the change of internal energy for the iron. It will be exactly the same formula, but with the mass of the iron, heat capacity of the iron, and of course, a change of temperature. Then let me see what to write. Maybe I should write here. Thermal mass for the iron, 1 gram or something. 5 grams. Let's put 5 grams of mass. 5 grams. We can convert to kilograms, of course. It will be mass of the iron, heat capacity of the iron, taking constant, change of temperature of the iron. Let's put that here, water, and this iron. Then, I know the initial temperatures. Now I apply the first law of thermodynamics. Let's write here, I think the video can clearly, I will close this. Let's apply the first law of thermodynamics here. At the end of the day, it will be the change of internal energy of water plus the change of internal energy, iron, is equal to 0. One is the negative of the other. Then let's replace the values. It will be 1 kilogram for the water, multiplied by its heat capacity, 4,200 joules, kilogram, degrees Celsius. Change of temperature is final temperature, which I don't know what is. Initial temperature, which is 20 degrees, plus 5 grams divided 1,000 for converting to kilograms, multiplied by the heat capacity of the iron, which is 450. Actually, if I had not converted this, I could express 0.45 actually. Well, anyway, I did it this way already. So 450 joules, kilograms, degrees Celsius. Change of temperature, final minus 110 equals 0. Then if you see the units, kilograms and kilograms cancel here, grams, kilograms, kilograms. And the final temperature you will find in degrees Celsius. Then, of course, you will solve this yourself. I mean, copy these equations. And at the end, some clues about the result, because it's not only obtaining the result, it's looking if the result has logic. First, between which values the final temperature has to be? Between 110 and 20. If you obtain 5 degrees, wrong, you did something wrong. If you obtain more than 110, it's wrong. If you obtain in between, okay, closer to 110, closer to 20, well, it depends on the amount of mass. Obviously, there is more water, and the temperature of the water doesn't change so much in comparison with the temperature of the metal. So what I would expect is that the final temperature to be closer to 20 than to 110. That's what I would expect. Then, of course, you will copy this equation and you will solve yourself there. I think it's not a difficult problem. And then it's done. Now let's talk about change of entropy in this problem. If I want to calculate the change of entropy and verify that the second law is satisfied, what should I do? Don't worry, you can solve that later. Well, let's talk about the entropy first. Then I will delete this part because it was the first law. The process of solving the problem is more important than the result. I mean, if you know the process, you can solve the result. Now there are some, of course, inconsistencies in some programs. The university has to work on that, especially in some faculties. For example, when you start to analyze some courses where you need statistics, but you have not seen statistics, obviously the students were struggling. That happens. But here, I think everything is consistent with you. I think your background, the way how the program is designed in environmental science is perfect, I think. They did a good job, tremendous job here. Sorry, I was talking like Sean a little bit. That's for imitating, for joking a little bit. Then let's put it this way. The change of entropy, total change of entropy is the change of entropy of the iron plus the change of entropy of the water. Right? Then let's calculate the formula. It will be the integral. Well, I don't know how is your mathematics, your calculus, or what's up, but let's do it. It will be mc dt divided t between initial temperature, final temperature. Because this is the change of heat divided by the temperature. This will be for water. Water plus well, let's put iron because I put it for consistency. Let's put iron. For water, let's put water here. Water, the T temperature is equal to, what is the integral of this? The T divided T, assuming C constant, this integration gives the natural logarithm. So at the end is mass of the iron, C iron, natural logarithm, final temperature divided initial temperature plus mass water, C water, natural logarithm. And then something, of course, when the final temperature is larger than the initial temperature, this fraction is larger than 1 and the natural logarithm is positive, which is what happened to the water. The water final temperature is larger than the initial temperature, so it gets entropy. In the case of iron, it loses entropy because the final temperature is lower than the initial temperature. If you know the natural logarithm, you remember the natural logarithm, no? So if you don't remember Wikipedia, natural logarithm, and you see the figure, the plot, you will see that when this fraction is smaller than 1, the natural logarithm becomes negative, okay? Then this has to be larger than 0 for satisfying the second law of thermodynamics. You will calculate yourself. Later, I will give some time when I finish the recording. I will give you some time to solve maybe the last 10 minutes of this half session. Still, we have 5 minutes before those 10 minutes. Okay, and then after we come to phase transitions and so on. This is just an example. So copy this. I don't know if you take a photo or whatever, but because you will find the final temperature and you will calculate the change of entropy with the information. You had heat capacities, you have the temperature, you have the masses. Okay, excellent. Right. So now I will put another example, a piston. Well, there is a basketball team called Detroit Pistons, but not that Pistons. I'm talking about the real Pistons. Then I will delete here. Can I delete this? Okay. Well, I will make a parenthesis here. What happens if I put an ice which has minus 4 degrees Celsius, and I put it in water, which is, let's put 80 degrees Celsius. Well, this process is more complex because there is a phase transition in between. Here's the ice goes from -4 to 0. That's calculated normal with the formulas we saw. But after this, a latent heat. There is a latent heat due to the phase transition where the ice absorbs heat without changing temperature. So it remains in 0 degrees for some period until it changes phase. That's what the phase diagrams will tell you later. I will show you later. And then after, when it becomes liquid, is when it starts to increase the temperature again. So there is a gap during the phase transition process where there is no change of temperature. Okay? That's an issue. Okay, the pistons. Let's go to the pistons. Let me delete this. Because pistons have applications in many areas. Basically, mostly in mechanical issues, but let's talk it here. You have a piston. This is the angular velocity. You input heat. Let's put 300 joules. And I want, do you remember that we defined the work for a piston? The work is minus the integral of pressure times differential volume. Let's assume constant pressure process. Constant pressure process. What's the name of the constant pressure process? You forgot? Should be isobaric. Isobaric. Okay. Anyway, the name is not important at the end. Important. So at the end, this minus P change of volume. Initial volume, final volume. The final volume is larger than the initial volume, then the work is negative. And I want to apply the first law of thermodynamics for knowing the change of volume. Or I could ask instead for a fixed change of volume, what is the pressure? Constant pressure felt by the piston. The pressure will not be constant, of course. Will not be because it changes, but it's just an idealization here. This approximation is valid under some processes. Then let's assume in a thermodynamic cycle, I want to calculate the pressure, giving a change of volume of something not so exaggerated. 1 meter cubic for simplicity, okay? 1 cubic meter, like this. Then this is the amount of heat in the thermodynamic cycle. How do you calculate the pressure in that case? First law of thermodynamics again. The first law is telling you heat plus work equal, in this case, 0 because it's a cycle. Then, of course, the heat is minus the work, and the work is this. And the minus and minus is plus, it will be pressure, change of volume. So the pressure will be heat divided change of volume. Then you replace here 300 joules here. And here you replace 1 meter cubic. Remember that the pressure, the units of pressure is what? Pascals. And the pascals is what? Newtons divided meter squared. Is the force per unit of area. Remember, your shoes, when you have shoes, if your shoes has a wider platform, what will happen? The force will be distributed in a larger area, no? You want?
So less pressure.
Less pressure, exactly. So, I mean, this is important. The concept of pressure is very important. The reason why a person, when it's collided with a car or the car stands over the person and it's very painful or whatever, is because, of course, the area is not large enough to distributing the force and reducing the pressure. No? That's very important. So these units are consistent. Joules is Newton, meters. This is meter. At the end will be newtons divided meter squared. So just replace it and you find the pressure. Yeah, that's it. And in pascals. Then now I will start the recording. This is part of the review of the last time with some examples, some problems in the exam. I will ask these kind of problems, plus some problems where we include first order phase transitions, which I will explain after the break. Then I will stop the recording for giving you time to find the final temperature and the change of entropy of the previous problem. So let's stop this recording.